complicated to work with just wave models, but sometimes waves not enough, and so in those cases it can be important to consider the interaction of different models together. So that would be the atmospheric circulations, the ocean circulations, the ice, and so when this becomes too complicated, I decided that I wouldn't do it myself, and so I was happy to have the help for many nice people from you. So Anne-Claire was one of postdocs who worked on this. Matthias did a PhD also working on ocean wave interactions, and Joris is now picking up the torch, working with the coupling with the atmosphere. So we will. So Joris will give you after these slides some more details about how we do the coupling today with the OASIS, and that can be used with the version 5.08 that we're using now. And so what I will do here is to introduce the general reason for why you want to look at some coupling and some examples, and a bit of theory behind that. Yeah, so why worry about coupling? So the essentially the waves, they're associated with the motion of the surface, but it's moving, not the surface which is moving, the air is moving, the water is moving, and if you have sea ice on the surface, the sea ice is going to be moving. And of course, if you're in shallow water, the wave is going to stir up the sediment, it's going to change the ripples, the moving of the blocks, it's going to change turbulence in the bottom boundary layer. And all these effects, in some cases, can introduce some feedback. So, for example, you know, you see the waves are blowing, the wind is blowing, make some waves. That changes the roughness of the sea surface, and so that can change the winds. And so, if you're computing the waves from the wind, you know, maybe at some point you need to consider that the wind has been modified by the waves and take that into account. The same thing with the bottom, and also there's a lot of wave activity at the surface, which introduces a lot of mixing. And the coupling really becomes relevant when this feedback becomes important for if you're studying waves. If the modification of the wind or the modification of the current is important for the waves, then maybe you have to introduce some coupling and then run two models together, or find some ways to exchange the information. And there's many different methods for doing that. Some people write files. There's some virtual files in memory. There's can be some other things. And also, if you're not so much interested in the waves, but in the wind, but you see that the waves are important for the wind, then maybe you need to couple the wave model to your atmospheric model. And so this is what some people have done. And so today, the most advanced coupling on the maybe not so much on the theory side, but on the practical application is really coupling with the atmosphere. And this goes back to the late 80s and early 90s. And people, yeah, so this is what happened at the sea surface with some details. I took these slides from a colleague in the US, Jim Doyle. You have, typically you imagine you have wind blowing and the flux of momentum. So as the wind blows, you have some mixing in the air, and you also have some wave generation. So you have a flux of momentum, which is putting momentum in the ocean. This flux of momentum is not quite constant. It's not a constant flux layer, because some of the momentum actually is taken up by the waves. And so the wave stress, the wave supported momentum increases toward the surface, and right at the surface, most of the momentum is carried by the pressure times the slope of the sea surface correlations. So if you imagine when the wind blows, you have a stress on the sea surface. It's not like it's a flat table and you're just pushing on it like that. It's just you have hills, which are the waves on the surface, and the correlation of the pressure on the slopes is like the form drag, which actually carries most of the wind stress. So the sum of this and that is actually constant flux, but the details of how this happens can change the resulting drag. The very complicated nature of the surface is that, okay, so you have some waves. It's not just nice sinusoidal waves like you could treat theoretically. They can be steep. Some of them are breaking, and there's usually with breakers you have an airflow detachment behind the breaker, and which will introduce a bigger foam drag. And so at high winds, most of the foam drag is supported by the breaking waves, and we have no theory for that. only empirical adjustments to the well, the general theory that yes, you have some form drag, and how you parameterize that or how you treat that is fairly complicated. That's for the air side. Something which is not on this page is that, of course, the breaking wave will generate some droplets, spray. So we have at very high winds, typically above 25 meters per second, the sea becomes more and more white, and the air becomes more and more foggy because of the spray. And actually, you have a change in the density of the air because you have water droplets in it, right? And that changes a lot the airflow, and that can be very complicated. It's very important for the heat fluxes because the latent heat of these droplets and all that stuff. So this, people that study hurricanes, they work a lot on this problem. Now, on the water side, these breaking waves will generate some eddies, turbulence, mixing. There's stabilities that combine this turbulence with the wave motion. So the wave motion is almost, well, yeah, from a Lagrangian point of view, is periodic, but from a Lagrangian point of view, the water particles actually drift. And this drift is more intense at the sea surface, and we have a shear of the drift, and the shear of that drift interacts with the turbulence, and that will generate these funny rolls that are aligned in the wind direction, which are called Langmuir cells, and that appear most of the time. And these are very important for defining the mixed layer depth and training whatever stuff you have in the sea surface. Yes, this is pictures from Fabrice Véron, and there you can find different flavors of that with sea spray with bubbles inside. And so, of course, as waves break at bubbles in the water, and also the bubbles in the water, they change the density of the water, that can introduce some stratification. And some people are having a lot of fun. There was a very nice conference in Seattle a couple of weeks ago dealing with all this stuff. So in terms of wind in the atmosphere, so people have been, so on the US side, they've been mostly worried about hurricanes and the forecasting of hurricane tracks. And this is, to give you an example, so if you look at the wave spectra, these are the different wave spectra around the hurricane. So you can see these are the ISO lines of ISOTAX, the line of wind speed. So above 55 meters per second, it's category whatever, that's category 5 hurricane, I don't remember. Anyway, so the strong winds on this side of the hurricane, so in the case of Hurricane Ivan, so the hurricane is moving in this direction, and in this region on the front right corner in the northern hemisphere of the hurricane, you typically have very strong waves because they're moving away from the hurricane. And then on the other sides, so on this side of the hurricane, here the wind is blowing this way, so it's going against the swell, or it can go. So the hurricane is overtaking swell that has been generated previously, so the wind can go against the waves. And on this side of the hurricane, you typically have multiple peaks and a very cross wind pattern. And these different sea states actually have very different drag coefficients, even for the same wind speed. And there's some interesting papers recently by Ed Walsh and Leo Oltheisen from Delft. And they've been trying to look at how you can parameterize the drag coefficient as a function of the directional distribution of the wave energy. Some of the studies, okay, these are examples of measurements of the drag coefficient. So the drag coefficient is a coefficient that goes in front of the wind speed squared to give the wind stress. So the wind stress at the sea surface is a drag times U10 squared. That's how it's defined. And another way to look at the air-sea coupling is to define a roughness length, saying that you have a typically log layer type of boundary layer, and then the profile of the wind speed in the boundary layer and the wind stress is going to be related to this roughness length. And we have different parameterization for that. And some will give you, pretty high values at high wind speeds. So this large endpoint extrapolation from 1981 is completely unrealistic compared to the measurements. And this is a drag coefficient that corresponds to this roughness length. And so most of the observations tend to show that the drag coefficient doesn't go above 3 times 10 to the minus 3. So CD times 1,000 is less than 3. But there's a lot of scatter. And at low winds, so this is only from 20 to 50 meters per second. So it's a really strong wind. So this is 40 knots, this is 100 knots. Okay. We have very little data there, of course, and at low wind speeds, not on this chart, there's a lot of scatter also due to the presence of swell. This is adapted from Powell et al. To the paper in 2003. So people have measured that also in the lab, so you can measure the drag coefficient with increasing wind speed, and you get different estimates using different methods. And going to very high wind speeds in the lab is always a challenge, because usually in the lab you have a ceiling, and when the wind speed gets too fast, then the boundary layer from the ceiling touches the boundary layer from the bottom, and so lab measurements, you should always take them with a grain of salt. In the field, it's not so easy either. Some people have used drop zones. They drop an instrument which has a GPS on it, and the motion, the drift of the instrument as it drops down, so they know how much it should move with the wind speed, and so they can try to estimate the wind profile from that. And so these are the only reliable measurements in high wind speeds, and of course some people don't agree that these are good measurements, so there's a lot of debate about that. And in that case, that gives you this drag coefficient which goes only up to 3 times 10 to the minus 3 at wind speeds of over 20 meters per second. So these are the kind of issues that people are looking at for the air-sea coupling. And so these are typical results with the QAMS model developed by Jim Doyle at NRL in the US, coupled, well, coupled or not coupled with some waves and with different parameterizations. And so this shows the drag coefficient in the case of the Francis hurricane. And so in this case, you have no wave feedback. So it's the drag coefficient is only a function of wind speed. And here, the drag coefficient will be enhanced when the waves are very steep. And you can see that the hurricane looks quite different, the structures, the rain bands, yeah. So, coupling can change a lot the structure of these things. Another example of application is for looking at storm surges. And Lucia has been working on this recently, so she had the papers Ocean Dynamics last year or something like that, looking at some big storms in south of France. This is an earlier work by Mattenbroek, who was doing his thesis on this question at KNMI in the Netherlands in the 90s. And he was doing some coupled runs with a wave and storm surge model, and the coupling was done by changing the stress in the that feeds the storm surge. And so in that case, he had the dashed line was the Smith and Bank drag coefficient, and if you replace it with the this one here, Smith and Bank, and the dotted line which is above here takes into account the facts parameterization of the changing stress as a function of the wave age, and the observations are the solid line. So essentially, it has an enhancement of up to 20% of the surge due to the wave effect, and this has been repeated in other places. Interestingly, part of the abstract was saying, well, most of the improvement can be reproduced by assuming an overall increase of the roughness. So if you replace the Smith and Bank by a Toronto coefficient with a constant Toronto coefficient which is higher than usual. So usually the constant over the oceans with a constant, right, quote unquote, is 0.018, and if you put 0.03 in the North Sea, well, yes, it gets a very nice result. The problem, so maybe you don't need to do coupling, just adjust the coefficient, but you have different coefficient in the North Sea, a different coefficient in the Bay of Biscay, and another coefficient somewhere else. So yeah, maybe having, and this is conclusion, a wave-dependent drag is to be preferred for storm surge modeling. And that was 1993, 22 years ago. And still, there's a lot of people that run storm surge models without any wave-dependent drag, just because it's, it can be a nuisance or it's more work because you have to put a wave model and blah, blah, blah. But, if this is what you need, then you just have to do it. So giving also some more example on the drag coefficients, these are plots from ETMWF. So this is, so ETMWF is the I think still, or maybe the Finnish Met Institute has done it also. It's the only place where they run operationally a wave model compared to the atmospheric model. And the reason is this one is that for a given wind speed, the drag coefficient in their model varies quite a bit with, and the variation here is mostly due to the wave age. So if the waves are young, meaning that they're still small and the wind is forcing them strongly, so they're in the growing phase, then it's usually more rough and the CD is higher. If the wave is more mature, you have a longer stretch, then the CD will go down. One of the issues is that, so this is the ECMWF model before 2011 and after 2011. So they changed something in their model, and that changed a lot the distribution of the CD. Apparently, the forecast, the atmospheric forecast, was better with this one. And the question is, okay, is this big change in drag coefficient realistic? Because they really go from at 25 meters per second, this stuff goes up to 5 10 to the minus 3, which is much higher than any observation. So there's a big debate on whether this is realistic or not. It seems that it's giving better atmospheric forecast. One of the drawbacks, it's also giving lower wind speeds at high winds, and this is, I think, the main reason why the ECMWF winds are lower than the NCEP winds is because of the coupling with the waves. So maybe the stress and the atmospheric evolution is better, but the wind speed seems to be a bit too low. And so, well, part of the work of Lucia is actually now to try to see if we can improve on that and maybe have something which gives maybe a bit smaller CD, but the right distribution of CD. So that was from the atmospheric side. On the ocean side, well, again, most of the momentum that goes from the wind to the ocean is going through the wave field, especially at winds more than 10 meters per second. And so if you imagine that you have an atmospheric front passing, which is an example of time series of the wind, that would be the wind stress coming from the atmosphere, and some of the momentum which is coming from the wind is actually going away with the waves. It's not everything is dumped locally. So here you have a front passing, so the wind speed drops from 80 meters per second to 10 meters per second, and the wind is turning. And the wave model, if you believe it, would tell you that instead of the wind dropping right away, you still have some momentum going to the ocean because the wave has some memory. And this memory for the stress can go for 5, 4, 6 hours. So instead of forcing your ocean circulation model with just the wind stress, maybe you should force it with the wave stress, and that wave stress will be less variable than the wind stress. So that's for the momentum in red here. The momentum flux going from the waves to the ocean, and the other curves are for the energy. And of course, the momentum is, in terms of waves, it's the energy divided by the phase speed. So the momentum is mostly carried by the short waves, whereas the energy is carried rather by the dominant waves. And so the relaxation time of the long waves is longer than the short waves, so it's longer for the energy flux to go back to balance. And you can see that the energy flux can be 3 times larger than what you would have if you just use local wind. So if you're looking at mixing of the ocean, the thing can be out of balance for 12 hours, 24 hours. So there's a lot of energy in the wave field that can be a memory buffer and change the upper ocean mixing. That's model view. Is it real? That still has to be shown. In some other cases, we know that the currents have to wind stacks on the waves. Maybe you don't include some couplings. This is an example from just outside here, in which we're forcing the wave model with the current. In that case, it's not coupled, it's just forcing. And we went, so the observations are in black. The model without current is in green, and the model with the current is in red. And you can see it follows here up and down, more or less, the oscillation of the wave height, which is due to the tidal currents. And this is a case where the buoy is here, it's just 30 kilometers this way. And that's the case with our biggest, latest storm was March 8, and we had a lot of damage on the coast here. So here, maybe So the question is a change in wave height going to have any impact on the current with tidal currents in 50-meter depth? I don't think so, but we haven't tried, so we don't know. And so it's more than that. Also, in shallow water, when you go to the beach, another example of so here you have the depths and different sensors. This is from Duck from the east coast of the US. So the offshore is here, the beach is on the right, and what you have here are time series at different sensors from offshore to close to the beach of the wave heights. And so here the oscillation you see here of the wave heights is essentially the modulation due to the water level. So here we are forcing the wave model with the change in water level, and the change in water level is changing the braking. The question is, okay, do we need to also take into account the feedback of the waves on the water levels? In that case, probably not, because we're still in fairly deep water. But if you're looking at stuff happening right at the beach, and what's, actually, if you have flooding or overtopping, if you have a big storm surge with a hurricane, yeah, you need to update the water level, and so you need to have the waves on a higher water level, and the waves will change the water level, so you need to have a coupled system. And this is the reason why the USGS developed their COAST system, which is a coupling with SWAN, WRF, and ROMS, essentially for this kind of application on the beach. And another type of application we're just getting into is what's happening with the sea ice. So, again, if you take again this sketch of the flux of the momentum flux coming from the atmosphere, this tau. The stress here is a sum of different bits and pieces, because some of that stress is just viscous stress on the sea surface. Another part is the stress on the waves, essentially the form drag. So you have the viscous part and the form drag. But then when you have ice, you also have wind blowing on the ice. And if you're working in the marginal ice zone, it's only ice flows, only part of the sea surface covered by ice. Okay, so the stress that goes to the ocean, so there's that you have to remove, but then you need to add the stress which is coming from the wave dissipation, which is this one, all right? But also the waves are pushing the ice because they are being dissipated by friction below the ice plates, or also can have some wave reflection by the ice edge. So if waves go back, waves have some momentum. So it's like you have the recoil of the ice flows from the waves, and this is what actually leads to the formation of ice bands. If you look at aerial pictures or satellite pictures from near the ice edge, when the wind is blowing from the ice towards the ocean, the ice tends to form bands because on the edge of the ice band, the waves are pushing on it, and it's being pushed harder. And on the other side, you don't have that push. It tends to make the ice stick together, making bands. The funny thing, when they get inside of the ice, also the wave is going to break the ice. It's mechanical failure of the ice, and this is what defines the marginal ice zone. And as you break the ice, you're going to change the heat fluxes, and yeah. So here you go. So you have to change. So you're changing the size of the ice flows. You change the rheology of the ice, and so we're having a lot of fun with this right now. All right. So a few things about the wave current interactions before I leave the floor to Joris. Joris will talk more into the practical aspects of how these things are coupled. What's happening on the ocean side? So the wave, as I told you, from an Arrayan point of view, it's essentially periodic. But if you follow the water particles in time, it's a simple example of a monochromatic wave from t equals 0 to nearly half a period later. So the crest is moving to the right. So the colors is the pressure, the minus the hydrostatic pressure is a deviation from the hydrostatic pressure. And the arrows are just the orbital velocities. All right, so this pattern is moving as the waves propagate, and if you follow water particles over 2 periods, so which is twice this time, it will make something like that. So it's not a closed orbit, but something which is stretched in time, like a cycloid, if you want. So that's the Stokes drift, and you can see that the drift near the surface is pretty large, and at the bottom it's almost 0. And if you do, you can do the same with nonlinear steep waves, and you get these kind of things. In shallow water, you get a very strong drift at the surface and a smaller drift below. So this drift of the particles, of course, going to be important for transporting material, and you really have to combine the mean current and Stokes drift in the right conceptual way to be able to do that. And so one way to attack this problem is to consider the Lagrangian mean drift of the particles. So you imagine you're going to follow the particles, but you want to attach this drift to a fixed position. So you take the water particles minus some mean current, and that gives you this Lagrangian. So you have to connect the Lagrangian way to the Eulerian way, and I won't go into the details, but it's a nice mathematical way for doing that is to use what's defined as the Lagrangian, the generalized Lagrangian mean. And so from our wave field, we can define here this thing. So we get this profile of velocity. There's a bit of a trick because when you do this transformation, the generalized Lagrangian mean, you're averaging at the position of the displaced particles, and so the waves, you have more waves in the crests you have more water in the crests than you have water in the trough. Okay, and so as a result, the mean position of the particles is higher than the actual mean sea levels. That's why you get this z equal d over L, which is this Lagrangian mean sea level. And so if you just do a small simple transform to put everything back in the right mean position, you get transformed GLM equations, which is what we've derived in a paper 2008. And so you can use these equations that gives you how the waves and the current should be interacting. All right. A simple case before we get to the 3D business is to look at a 1D. Just imagine everything is uniform horizontally, and you just look at what's happening in the vertical. You have a 1D model. In that case, you can write the Lagrangian mean velocity to be the sum of a quasi, or let's call it the current velocity, u hat, quasi-Eulerian, and the Stokes drift, us. And you have an equation for the current velocity, which is this, and the specificity of the wave effect that it introduces a Stokes drift here inside of the Coriolis force term. And this was later called the Stokes Coriolis force. And then you have this is a mixing. Okay, so imagine you have some stress at the sea surface, get some mixing, and you will get a current profile for that. So if you have no mixing at all, no mixing, then this equals 0, which means that u hat is equal to minus us, and then the Eulerian current would be exactly opposite to the Stokes drift. That, of course, is a time stationary conditions. If it's not time stationary, you can actually have inertial oscillations which are driven by the Stokes drift. And this was described in a paper by Klaus Hasselmann in 1971. No, 1970. There's been some debate on how actually we can observe that effect, and then there was some paper about that recently. That was part of the thesis of Nicolas Rascle. So we did quite a few tests and looking at the data set. So this is an example of a mixed layer. So we have the current which is trapped in the mixed layer. So here the wind is blowing in the u direction, so the current will be to the right of the wind, in the northern hemisphere. And so because of the stratification, the current is very strong near the surface, then it drops to nearly 0. And if you keep blowing, if the wind keeps blowing, the mixed layer is going to get deeper because of the mixing, and you'll end up with this type of profiles. And then we've had a lot of fun comparing the model to the observations and different theory. And you get kind of Ekman spirals which are transformed by the waves. So if you're interested, I think the best paper about this is really this one from Rascle and Alduin. Give a detailed analysis of that data set. The difference between the one from Poulton et al. Is that Poulton didn't consider the stratification and it was only a stationary profile, whereas the stuff changed in time, so you have a rectification of the velocities due to the changing in the mixed layer depth. All right, so that was 1D, and if you go to 3D, you get this kind of effect plus some other things which come from the horizontal gradients. And there's many different equations and several ways to look at this. And if you have 3D equations, so you have 2D equations, and in 2D things are pretty simple. I think everybody agrees. In 3D, there's been a debate, especially between Jim McWilliams and us on one side, and George Meller on the other side. Apparently, George Meller still doesn't want to give up. But I think that everybody now would agree that his approach has some problems. Essentially, there was a first paper in 2003 and some others, and so the big difference between these two approaches is in one case, you're writing equations for the total momentum, which is its Lagrangian mean velocity, u bar L. In the other case, you're writing an equation for the mean flow momentum, which is its u hat. And so the two approaches should be equivalent, and actually in the paper from Andrews and McIntyre from 1978, they show how to go from one to the other. And so that's a theory, but then in practice, it happens that this equation for the mean flow is much more easy to implement. And one of the reasons is that if you write the equation for the total momentum, a piece of the momentum is the wave momentum. And this wave momentum is doing some very funny things because waves are trapped in a waveguide. And I don't know if I have it here, but no, I don't have it here. There's one test case that we looked at of waves going over a bump, a bottom slope. As the waves go over the bottom slope, the momentum of the wave field has to go up. And so you need to define or compute properly this vertical flux of wave momentum. And this is not given by usual linear theory on the flat bottoms. You need to go to some crazy model solving the full Laplace equation to get this vertical flux of momentum. So if you're working on this world with a total momentum, you have to take care of this problem. If you live in this world in which you only consider the current momentum, then just let the waves do what they want to do. They do it very well. You don't have to worry with that. And you only need to worry about the flux of momentum from the waves to the current. In that case, it's much more simple because you don't have this funny flux of wave momentum. And this is the main reason why the equation from McWilliams et al., which are equivalent to the one we derived from the DLM, actually give consistent results. And here they are. So this has been implemented in quite a few ocean circulation models now. So the first person I know that did this was Nicolas Haskell, who was working the version of RAMS. Then it was done by Yusuke Uchiyama at UCLA, also working with another version of RAMS. And then we had Anne-Claire did that in Mars 3D 4 years ago or more now. It was done by Matthias in the Portuguese code Mohid. It was done by other people in some other code. So I think, yeah, now many models have this stuff included. And so the difference between the traditional ocean circulation models is that you have essentially three terms. So one is this vortex force, which is a product of the vorticity, and this P here is a Stokes drift, which means that if you want to force an ocean circulation model with these equations, you need to know the 3D Stokes drift profile. The other terms are essentially some modification of mean pressure by the waves. The simple version, if you neglect the vertical shear of the current, is depth uniform, and so in WaveWatch it's called the Bernoulli head. This was introduced by Jim McWilliams. So you have a Bernoulli head output for WaveWatch that you can use for driving your ocean circulation model. And then you have the wave. This is the momentum lost by all dissipation processes. So when waves break or there's a friction on the bottom, you have some momentum flux which is going to the ocean. And you can specify that for the breaking term as a surface flux, and for the bottom friction as flux on the bottom boundary layer. And so these also are terms that are part of the output field. So we have these 90 possible nameless list of output fields. So some of these are related to the momentum flux due to braking. And so in WaveWatch it's called is at FOT. I forgot. So we get a TOT for the momentum flux, and for the energy flux, I think it's called FOC, but that's in the manual. We can check that in a second. So this is just a two-component vector. This is a scalar. This guy here is going to be a 3D vector. So to compute this one, what we did initially is to output the spectrum, the spectral distribution of the Stokes drift, so that then you can, if you know the levels of your 3D model, you can recompute what would be the profile of the Stokes drift on each level. If you don't want to go through this crazy business, you can use an approximation from a colleague, Øyvind Breivik, has been working on this at SimWF, and he came up with a parameterization of the profile from the surface Stokes drift and the Stokes drift transport. And actually, part of the wave arch output are these two things: the surface Stokes drift is a vector, two components, east and north components, and the transport due to the Stokes drift. And so Øyvind has a paper in APO last year in which he parameterized the full profile from these two quantities, the surface values and the transport. Of course, if you have a funny spectrum with multiple peaks, it will not be exact, but at least if you want to play and try that, it's probably easier than carrying the full 3D array of Stokes drift values. Oh yes, it's not over, because yes, there's also mixing in the ocean, and the mixing in the ocean is due to the energy coming from the wave breaking and the energy coming from the bottom friction. So these are the reasons why we also output the fluxes of energy, not just the fluxes of momentum. And you can, okay, and then what you do with that, typically you can plug that in your mixing scheme in the ocean model, and you cross the fingers and hope it's going to be giving the good results. And you can talk to Anne-Claire, who's been playing with that quite a bit. The basic idea is that you have some extra TKE coming from the waves, and so you have a turbulent kinetic energy equation. You have an extra source coming from the waves. In reality, it's not like waves and turbulence are independent, and there's more complex effects, and all that. So this is a version of the equation from 2008 paper. It's consistent, at least in the first order of the shear, with the equation of McWilliams et al. 2004. If you go to very strong shear, there are some differences. And if you're really interested, we can talk about it. All right, so these were the first results with a 3D model from the surf zone. This is an example of waves going at the beach. This is from the PhD thesis of Nicolas Rascle. So you have a longshore current. So the waves are coming at an angle and they push this longshore current. And this is a profile of the current as a function of the crossroad distance. So here, the middle of the surf zones, we have a current of 0.5 meter per second. And if you do a 2D or 3D model, you'll have different different current profiles, and the vortex force actually tends to push the current towards the shore. That was one of the conclusions of Nicolas. These are other 3D models that was done at the University of Oregon by the group of Berger and Allen. It's a paper in JGR 27. So here you have profiles of current driven by the waves, and this is compared to measurements in the arrows here. So this is the cross-shore velocities. These are the long-shore velocities. So you have the long-shore current is strongest in that area, and then you have a weaker current offshore. Yeah, and it's not perfect. The story is not over, and so there's people who want to do a PhD on this. We can talk again, because the turbulence is actually modified by the waves. And so the turbulence closure that you are used to, doesn't quite apply in the presence of waves. And this was shown very nicely by Jaco Groeneweg, who's part of his PhD work, again at Delft. And this shows profiles of, in vertical here, of velocities. The solid line is in the middle here with the symbols, is a profile of the current without the waves. And if you have waves following the current, then the current changes the profile. You have a profile like this. You have a weaker current at the surface. And if you have waves opposite the current, then the current gets actually stronger at the surface and weaker at depth. There's been an attempt to reproduce that with different models. So here, the model here is from the Jaco Groeneweg thesis, so the couple of papers in TFM. This uses a fairly involved treatment and rewriting of the mixing scheme, taking into account the distortion of the turbulence, by the way. So as the wave passing by, the turbulence is modified on the scale of the wave period. There's a similar work that was done by TCMA at MIT, in which he used the parameterization of the modulation of mixing by the waves, which seems to be giving good results. There have been some other attempts, and I know one by, I forgot the name, Portuguese student that was working half in Portugal and half in Paris, using LES type model to reproduce that. But it's, yeah, these things will still have some issues to reproduce it. And if you don't have a special mixing scheme that takes into account the wave effect, you will not be able to get these changes in the wave in the current profile. So there's still a lot of research in this wave current business. And I think I'm going to stop there. And that's the so-called old approach of how to couple the waves and the current models using Palm. And so you can ask Anne-Claire and read the papers if you want to see more details. So the use of Palm on paper was really nice because it was meant to be able to couple 3D models and all that stuff. In practice, it's fairly, well, it is a little complicated because you have to compile WaveWatch as a subroutine and then recompile it together as a module with your other model and some other stuff in between. And what Joris will show now is what we do with Oasis, which is another type of coupling approach. And that's, yeah. All right, so yeah, I've been maybe a bit fast. So if there's any question about coupling in general, and then Joris will just come up and